Okay, so the agenda for today would be like I'll be discussing like 15 or so problems of varying levels of difficulty. I believe the audience is around class 9th and 10th. So some of the concepts that I introduced might be very new and somewhat difficult for them. So let me know if you want me to go slower. I'll do that and stop me if you have any questions. Okay, so with that, some conventions and notation I want to set straight for at the beginning. So whenever I say the logarithm, I'll always mean base e. I hope you know what the base e is. Uh, then I'll refer to the trigonometric angles, and the arguments of those functions will be measured in radians. This is more convenient, somewhat convenient. And the conversion is given as this: 180 degree is pi radians. This is the conversion factor. And yesterday also I saw that the summation notation was introduced. And on top of that, I'll be using another notation, which is the product symbol. I hope these are standard notations by now. Okay, so moving on to the first problem. So I want to find all the values of n such that this sum is some power of 10. And so this is clearly an AP. I hope you know what is an AP. AP is something like this. Something that increases with a constant difference. Okay. So this is an example of an AP, arithmetic progression. So I'll use the property of the sum of an AP. Basically, I'll be summing over 1 plus 2 plus dot 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 up to some n. This is an AP with this d is called the common difference. So the common difference here is 1. And then I'll be using the prime factorization theorem, and congruence will be another tool that I'll be using here. Okay. So I leave it up to you to find the sum of this. You don't need to know the formula for summation of AP. It's a very neat trick to solve this kind of sums, but you don't need to know that. So I'll urge you to find this sum. The value of this sum is this, and we are asked that it should be some power of 10. So 10 to the power k. Also, another notation that I'll be using is this n0, where n0 means the natural numbers including 0. Okay. So how do we go about it? So basically, I can break up n times n plus 1 as this, and I can break it up into two parts, which are co-prime to each other. So the GCD of 2 and 5 is 1. So naturally, any power of 2 and any power of 5 will have GCD 1. And on the left-hand side, I see that a number and one incremented is always having GCD 1. So by uniqueness of prime factorization theorem, two cases can arise. Either n is equal to 2 to the power k plus 1, or n is equal to 5 to the power k. Okay, so these are the two cases that we'll be solving for. In the first case, I have this identity, and when I take mod 4, on the right hand side, I'll end up with 1. 5 is congruent to 1, mod 4. So any power of 5 will also be congruent to 1, mod 4. So the possible solutions are 1, 2, 3, and so on. Okay. So any power of 2, where n is greater than 2, is congruent to 0, mod 4. So naturally, this equation will be satisfied as long as k is greater than equal to 1. Okay. But then we see that if k is greater than 1, I can never satisfy this condition. That n plus 1 condition I cannot satisfy. Okay. So naturally, the only option left is k is equal to 1. And for k is equal to 1, I see that n is equal to 4. So this is the first solution that we get. And it is easy to check that 1 plus 2 plus 3 plus 4 is 10, which is 10 to the power 1. Okay. What about the other case? The other case is when n is equal to 5 to the power k. Okay. And again, using that n plus 1 is equal to 2, I put the value of n in this equation. So 5 to the power k plus 1 is 2 to the power k plus 1. I take mod 4 again. And okay, so you may ask why mod 4. So I see that 5 is congruent to 1 mod 4, and any power of 2 greater than or equal to 2 gives me 0. So it's a convenient choice, you can see. Okay. So on the left hand side, I'll end up with 2, and on the right hand side, I keep it as it is. So this congruency relation is only satisfied when k is equal to 0. And for k is equal to 0, n is equal to 1. And that is a very obvious solution. Okay. 1 is equal to 10 to the power 0. Okay. Any questions in this? Let me know if I go too fast. Okay. Stop me and ask me questions. Okay. So moving on. So you want to solve this equation in the set of positive integers. Positive integers 1, 2, 3, 4, and so on. So what are the key concepts that I'll be using in this? I'll be using something called the well ordering principle. If you have not heard of it, it basically says that the natural sets cannot go infinitely below. Okay, it has a lower bound, and that lower bound is 1. That is the well ordering principle essentially. So similarly, if you consider any subset of the natural numbers, they will always have a lower bound. Okay, and congruence, again, I'll be using the congruence property. And the third result that I'll be using is something called the Archimedean property, which is basically that you can compare any two real numbers. Okay, any two positive real numbers. They can be scaled up to some quantity, positive integers, such that this equation is satisfied. This inequality is satisfied. Okay. So what was the right hand side? So we note that right hand side is 2xyz. Clearly, it's an even number. I don't care what xyz is, because there is a factor of 2. It has to be an even number. So 2 divides 2xyz. If the right hand side is divided by 2, the left hand side should naturally be divisible by 2. It's an equality. So I have 2 divides x square plus y square plus z square. So this implies that either all of them are even, all x, y, z should be even. And the second possibility is that one of them is even and the other two are odd. So only then can I have that the sum together is an even number. But in either case, I find that at least one of them have to be an even number. And if that is the case, 2xyz should be divisible by 4. Okay. So 4 divides 2xyz. So 2xyz is congruent to 0 mod 4. So x square plus y square plus z square should also be congruent to 0 mod 4. And we know that a square number is congruent to either 0 or 1 modulo 4. You should prove this result if you have not already done so. And then in order to satisfy this equation 1, the only natural conclusion I can have is that x square, y square, and z square individually they are congruent to 0. It's easy to check. Let's say x square is congruent to 1, then this relation is clearly not satisfied. And similarly, if I have only 2 of them congruent to 1, then also this relation is not satisfied. Or similarly for 3 congruent to 1. Okay. So the only possibility is that each of them individually is congruent to 0 mod 4. Only then is this relation equation 1 satisfied. What this implies is that 4 divides x square, 4 divides y square, and 4 divides z square. So if I take the square root, naturally 2 will divide x, and 2 will divide y, and 2 will divide z. So individually x, y, z are all even. Okay. So I can write x as some 2x1, y as 2y1, and z as some 2z1. And then the original equation, that was x square plus y square plus z square equal to 2xyz, that equation now reduces to something like this. Note that even in x1, y1, z1, the original form is retained. So I can follow a similar type of argument that I have shown here in the first part of the solution. And I can repeat this argument over and over. After n steps, what I find is that I'll end up with something like this. But now I will demand something. Now I'll demand that n is chosen to be greater than each of x, y, z. I did not have written absolute values because x, y, z are naturally positive integers. We are trying to solve them in positive integers. So just for completeness, I've written absolute values. So I choose n in such a way that individually I take the maximum of x, y, z, and then I choose an n which is greater than that value. And this can always be done via the Archimedean property. I can always find an integer such that it is greater than given. You give me any number, I can always find a positive integer which is bigger than that given number. So if I have that, so clearly xn, which was equal to the absolute value of x by 2 to the power n, that is less than 1. Because notice that n is greater than mod x, and 2 to the power n is greater than n. So clearly mod x by 2 to the power n is less than 1. But I mentioned that by well ordering principle, the natural numbers has a lower bound, and that lower bound is 1. So I cannot find any xn which is less than 1. I cannot find any natural number which is below 1. So similar arguments hold for yn and zn. So naturally, this has no solution in the set of natural numbers. But instead, if we had wanted to solve in the whole numbers, including 0, there would be a unique solution which is 0, 0, 0. That is pretty much obvious. Okay, so any questions with regard to this? Okay.
Like, sir, how you have written x to the power n is equals to x by 2 to the power n smaller than 1.
Okay, so let's see what is x1. Let's see for x1. So x1 is x by 2, right?
Yes, sir.
Similarly, x2 will be equal to 2x1. I'll just repeat the argument that I had done here, over here. I'll repeat this argument. So similarly, I'll find that x2 is equal to 2x1, right? Sorry, x1 is equal to 2x2, sorry. Let me use a new page, maybe. Okay. So what I had done is, I had written x1, x is 2x1. So this implies that x1 is equal to x by 2. Now I told that I can repeat my argument because my equation is of the form x1 square plus y1 square plus z1 square is 2x1 y1 z1. So I can repeat the argument over again, and I can write x1 as some 2x2, y1 as some 2y2, and z2 as some 2z2. So what will be x2? x2 is x1 by 2, but I already know x1 from here. So I will have x by 2 squared. And if I repeat this argument n times, I notice that xn will be equal to x by 2 to the power n.
Okay,
You notice this 1.
Yes.
This is 2 and this is 2. So naturally xn will be x by 2 to the power n. Is it okay?
Yes, sir.
Okay. Okay, so moving on.
Excuse me, sir.
Yes.
Sir, the word which you have used here, the WOP, that is
The well ordering
some,
principle.
yeah, well ordering principle. Is this applicable to all the numbers, like real numbers, irrational, rational?
No. It's not applicable to integers, even to rationals, to irrational, or to real numbers. It's not applicable there. Only it's a property of natural numbers. And I don't like to call 0 a natural number, but if you want to call 0 a natural number, then it's applicable to that scenario as well. So it's something like 0, 1, 2. In this case, the lower bound is 0.
Okay, sir. Thank you.
Yeah.
Excuse me, sir.
Yes.
So can you show me the answer again?
Mm-hmm. There is no solution in the positive integers. You have any doubt in any specific step or something? Or
Sir, means hence by WP there is
yeah,
no
so
solution to this, and I will understood.
yeah, so you find that xn has to be less than 1, right? Because this quantity xn is x by 2 to the power n, right?
Yes.
So that quantity is less than 1. But there is no positive integer smaller than 1, right? So there is no such xn. So there is no solution to this equation. Is that clear?
Yes, sir.
Yeah. Okay, anything else?
No, sir.
Okay. Just a minute. Okay. So moving on. So I don't remember if you did something like this yesterday, but this is a problem for selecting combinations with repetitions. So you want to make some combinations, some selections, some arrangements with some repetitions. Okay. So you already know what is a arrangement, what is a selection. Now I'm trying to make selections which are allowed to repeat. So I'll set this in the context of a problem which is given by this. So you want to find all the non-negative integer solutions to this equation, x1 plus x2 up to xk is equal to n. Okay. So you can think of it in the sense that there are some, let's take a simple case. So k is equal to 3 and n is equal to 5. So you can think of it as 3 boxes and 5 balls. So all the 3 boxes are alike and all the 5 balls are alike. And you want to see how many ways you can fill the 3 boxes using these 5 balls. So this problem is exactly equivalent to this problem of arranging the sticks inside. Note that I cannot move this. Let me draw it in blue maybe. I cannot move this stick and this stick. It makes no sense, right? I'm not trying to put the balls outside the box. So this and I consider
So your voice is not
so I want to
clear.
see how many ways I can arrange this system. Am I not audible? Hello.
Sir,
Yes,
your audio is going very fast.
yes,
Okay. Is it okay now? Maybe some
yes,
internet issue.
Now it's
yes,
fine, sir.
Okay. Okay.
yes.
Okay. So what I'm trying to say is, I'm trying to solve for this equation. Okay. And this equation is in the context of a combinatorial problem, which is like you have some let's say n1 objects of some kind and 2 of other kind and so on. And there are total of n objects. And you want to see how many ways you can arrange this system.
Now there is a disturbance.
This problem of
Sir, not able to hear you.
I don't know why.
Yes, sir.
Let me check. Is it okay now?
Yeah,
Hello.
fine. Hello, it's fine. Audible, audible.
Okay. Mm, Hello.
Again, now audible.
Okay. Okay. Now it's moving as well. Okay. Some issue with the internet anyway. Okay. So what I'm saying is, you want to fill this 5 balls into these 3 boxes. Okay. And that problem is exactly equivalent to the finding the number of arrangements of this 2 sticks and 5 balls. But there is a caveat. I can change the balls among themselves without affecting the arrangement. Similarly, I can switch the sticks and I will not be affecting the arrangement. So I have to take into account that fact. And to do that, I'll just have to divide by the number of repetitions. So such repetitions. These are done in 5 factorial ways, and this is done in 2 factorial ways. So exchanging 2 balls will not be changing my arrangement. So I have to take, so there are some repetitions. So so I have to remove those repetitions. So I'll divide the total number of arrangements. This is the total number of arrangements. I'll divide it by the ways which are being repeated. So 5 factorial ways I'm repeating the permutation. So what I'm trying to say is, you consider X objects, you permute all of them at a time. So here the X objects are 2 sticks and 5 balls. So you have 5 plus 2 factorial such arrangements. But now the problem is that if I exchange this to ball, let's say this and this, I will not affect the arrangement. So I have to somehow take into account this fact. And the way to do that is just removing all the number of repetitions, such repetitions. And how many are there? So I can arrange these 5 balls among themselves in 5 factorial ways. And that I have to divide over. Similarly, I can exchange these 2 sticks without affecting the arrangement. So I have to divide by 2 factorial. Okay. Is it clear to you? What is the total number of arrangements now?
Yes,
After,
sir.
Yes, sir.
It's clear.
Yeah.
7C2 is.
Yes. So in general, if I have such k types of objects, distinct objects, the result will be this. Okay. You should check this result for a general system. I've shown you for a 2 system. You should check it for a general k system. Okay. Moving on. Yeah. Any questions? Okay.
Sir,
Yes.
sir, in the example which you have given, it
Mhm.
doesn't it that it has to be having a hint of probability here?
What do you mean by probability exactly? Hello? Hello?
Sir, your audio is not audible.
I'm asking, like, what do you mean by probability here? Like,
Sir, like it is having chances that the balls may not
uh-huh,
be in the balls which are giving like 2 in one box and 3 in another box.
right.
Like so, there may other ways like giving 3 in another box. I mean 4 in another box, 1 in another box.
Certainly, certainly. I've shown you one example of such an arrangement. I've not shown all the arrangements. All the arrangements are 7 choose 2, right? So there are too many of them. One such example is this sort of an arrangement. You could have 1 balls in each of this and all the remaining ones in here. So all such possibilities are there. But the key argument is that since the balls are all alike, all are red in color, all are same size, exchanging any 2 balls will not give me a different permutation, right? So I have to divide by such repetitions. How many of them are there? 5 factorial of them are there.
Okay, sir.
Yeah. Similarly for the number of sticks. So if I exchange the 2 sticks, I won't be affecting the arrangement. So I have to take into account that as well. So this is a very simplistic system that I've shown you, but you could do it for, let's say, k number of different objects, which was actually the question. So you have k different types of objects, or you can say k different boxes, and then you are filling in some objects. Okay. So that way also.
Krishna,
Yes, sir.
may I suggest that you take 3 elements,
Yes.
say ABC, and then arrange, and then finally AAC, taking A repetitions. Then the permutation arrangement is not affecting A and A. In
Sorry,
case of
sir. Could you repeat what you just said?
3 elements, say ABC,
Yes.
ABC, 3 elements here, ABC, and then you show them the arrangement that was shown actually in my lecture also. ABC, the six arrangements. Now,
Right.
if
Right.
B is equal to A, then what
Aha.
happens?
Okay. Yeah. Exactly. Exactly. So okay. Yeah. So you have already done this, like repetition kind of. Okay.
Yes, sir.
Fine. So do you want me to go through it again, or like I can go through the example sir is suggesting right now?
Sir,
So
it
you
would
can
be
proceed.
better.
Okay. Okay. So let's see how many ways we can arrange this. So these are 3 different objects. I'm arranging all 3 of them together. So 3 factorial ways, right? So what are the different arrangements I can have? So ABC, BAC, CAB. One is this. ACB, CBA, CBA. So these are the 6 arrangements. Now what you do is you set A is equal to B. So A, AC, AAC, CAA, CAA, and ACA, ACA. So now you see that this is the same thing as, and this is the same thing, and this is the same thing, right? Initially you had them different, but now they are all the same. So initially you had total of 6, but now because two elements are the same, you have to mod it out. So 3 factorial divided by 2 factorial, which is just 3 distinct arrangements you can make, which are AAC, CAA, ACA. These are the 3 distinct arrangements. But if you had all distinct objects, you had 6 such arrangements. So this is what sir is suggesting. So same thing is what I am also doing. Because these objects are alike, exchanging the 2 won't make any difference. And how many ways that I can do that is number of ways I can arrange those objects among themselves. That's the way. That's why 5 factorial and 2 factorial respectively.
Sir, if the colors of the balls were different, so then
You have
like,
distinct
we would
objects,
not
right?
have, there would be distinct objects, and then we would not like to would not have to
Yes.
divide, right?
Yes, yes. Now then you have this
By
category,
5
right?
factorial.
You have
Yes.
ABC kind of example.
Yes, sir.
But then once you make all the colors same, you have something like this. You have chosen them to be the all same. Like you cannot distinguish A with A, right? So something like that.
Okay, sir.
So here you could distinguish AB and BA, but here both are same. So you cannot distinguish the two. They are the same arrangement. Okay.
Okay, sir.
Should I move on, or are there any further questions in relation to this?
Sir, you can carry on your view.
Okay. Okay. So yeah, so this is a somewhat more difficult problem, and it will use some ideas from probability. Okay. So what is the problem? So we are trying to collect a set of n different cards. Okay. And we get the, let's say we get the cards by buying some boxes of cereal or some chips or something. And each box contains exactly 1 card. So we cannot have any sort of funny things going on. With 1 box of cereal, you get only 1 card. And it is equally likely to get any of the n cards. So the probability of getting, let's say I have said numbered cards, 1, 2 up to n, or let's say I have some A1, A2, so on up to AN. So I want to say, what is the probability of getting A2, let's say. So it's exactly 1 by n. What is the probability of getting A3, or let's say AK for some k? It's always 1 by n. They are all equally likely. That's what it means. So the question is, on an average, how many boxes do we need to buy until we have collected all the cards and we have at least 1 copy of every card? Okay, that's the problem. So something that's that you'll need to solve this problem is something called a geometric distribution, which I'll explain right now. Then you need what is the notion of a probability. So probability is the favorable number of outcomes to your, let's say you want A2. So there is only 1 favorable outcome, right? And then divided by the total number of outcomes, which is n in our case. And then you need something called the expectation value, which I'll explain. So I think you have done addition and multiplication principle, which says that when 2 things are mutually exclusive and when 2 things are like independent and so on. So I need what is the meaning of an independent outcome. So let's say I talk, okay, I'll explain what that is. Okay, so first we consider a simpler version of this problem, and simple, a coin is tossed. A coin which is unbiased, it has equal probability of getting a head and an unequal probability of getting a tail. So a coin is tossed until a head appears. Okay, so this is my event, like until a head appears, I keep on tossing the coin. So and the question that arises, equivalent question that arises is, what is the expected number of tosses, or on average, how many such coin tossing I have to do to get a head? Okay, so what are the possibilities? Let's say I get head at the first turn itself. Like I toss a coin, I get a head, I'm done. I'll stop. Then it could happen that on the first tossing, I did not get a head, I got a tail, and in the second one, I got a head. So I'll stop at the second event, second tossing. Similarly, I could stop at third, I could stop at fourth, and so on. What I meant by independent event is the following. When I toss the first coin and I toss the coin again, the outcome on the second one is independent of what I have obtained on the first one. I don't care what I had obtained on the first one. So the outcome, if I tell you people to toss a coin, whether you end up with the head or tail is independent of what the other student will obtain. So that is the meaning of an independent outcome. In case of independent outcomes, the probability just multiply. So the probability of this event is 1/4 because the probability of getting tails is half and the probability of getting a heads is half. So the probability of the total event is 1/4. Similarly for the others. Is it okay? This step, is it fine?
Yes, sir, it's fine.
Okay. Now I'll define something called a random variable. So what is a random variable in this coin tossing experiment? It's just a variable which denotes how many number of tosses we have done or how many tosses that is required to get a head. So that is an example of a random variable. So this random variable, what are the values it can take? It can take 1 for the first, this case it will be 1. In this case, x will be 2. In this case, x is 3 and so on. So what is the probability of getting n? What is the probability that we require n times to toss the coin? So that is first n minus 1 times you get a tail, which is half to the power n minus 1. And then on the nth, we get the head, which is half. So since they are all equal, it doesn't matter. So it's 1/2 to the power n. So whenever such a distribution occurs, this type of distribution where the unfavorable event occurs n minus 1 times and the favorable occur on the nth turn or on the nth experiment, then such a distribution is called a geometric distribution. Okay. And if the probability was p, let's say instead of half, then we say that the geometric distribution has parameter p. In our case, it was half. And we denote, this is the notation, standard notation. X is some curly sign, geo of p. Okay. So this is an example of a geometric distribution. So x is equal to n. For the first n minus 1 experiments, I get an unfavorable outcome. And on the nth one, I get a favorable outcome. So that is an example of a geometric distribution. Now, what is expectation value? So expectation value is just the value of the random variable. This is the value of the random variable 1 times the probability with which it occurs. So essentially, E of x is equal to summation over, let's say, x is equal to 1 times probability of x is equal to 1 plus x is equal to 2 times probability of x is equal to 2 and so on. So what is the value? So here my random variable took values 1, 2 and so on. Sorry, 1, 2 and so on. But it could happen that it takes some other values as well. So whatever that value it's there times the probability with which the value occurs. So that is, and you sum up over all such possibilities.
So like E of x, is it a function we can say?
Yeah, you can think of it as a function, but yeah, I mean, it has a very well-defined definition. Even random variable is kind of a function, but yes, you can think of it as a function of the random variable. Okay. So it's just the random variable x times the probability of x. All possibilities sum over. So if you do this summing, you will end up with this. In our case, p is equal to half. Okay. And if the probability of x, some favorable probability is p. So you see, we have just two outcomes, favorable and unfavorable. So favorable probability is p and unfavorable probability is 1 minus p, because probabilities, total probability always sums up to 1. Okay. So unfavorable probability will be 1 minus p and the favorable is half. In our case, because the coin is a fair coin, p is equal to half and 1 minus p is also half. So you should find this sum. It's a homework for you. So this is the expectation value of x. So for our coin tossing experiment, on average, we need 2 coin tosses to get a head, which is very much intuitive, right? So head has only two faces. Sorry, a coin has only two faces, head or tail. So on average, we need two tosses to get a head. So that's what it means. That is very intuitive in some sense. Okay. So now we return to our original problem. Our original problem was a complicated version of this, nothing much. So in our case, we need to define what are the possible outcomes, the collection of the possible outcomes. So my suggestion is, let's start with sequences, which I denote as A, such a sequence, which the sequence takes values, right? And what values it can take? It can take 1, 2, and so on, up to n. Because there are n cards, the sequence A can take values in 1, 2, up to n, okay? But this sequence is not an arbitrary sequence. It has to satisfy certain criteria. One such criteria is each of the symbol 1 to n occurs at least once. Why do we need this? If you remember, we want to collect until we have collected at least one copy of every card. This is what we require, right? So I require my sequence to have all this 1 to up to n at least once. That's a basic requirement I need. The second requirement is I want the final symbol to occur exactly once. That was the minimum criteria, right? I need at least one. So I need that the final symbol occurs exactly once. I don't need more than that. So my sequences over this set should satisfy these two criteria. It cannot be an arbitrary sequence. I cannot just put any number I want. Okay. It has to satisfy these two conditions. Now, what is the random variable I should suggest here? A random variable can be the what values it can take. It should be the length of the sequence. What is the length I should go? Because I want to find how many boxes I want to buy, so that on an average I collect all the distinct cards, all the n distinct cards. So length of the sequence is basically how many boxes I am buying. So this probability of A is 1 by n to the power L, because each of the event occurs independently. What I will get in the next box is independent of what I have currently obtained. So the probability just multiply. Each event is independent. But unlike the previous case, our previous case, we had a very simple thing, right? We had heads, we had tail heads, tail heads, and so on. But in this case, to define the sequence of a given length is not easy. So we need to work around it. We cannot just take simple sequences like we did in our coin tossing experiment. So what should we do? So we should define our random variable suitably, and we will break it up into smaller random variables. Now I'll explain you what these smaller or simpler random variables are. RV, by the way, denotes a random variable, okay? So instead of looking at the whole sequence at a time, like I have collected all cards at a time, what I will look is only up to the ith card. So xi, what xi denote is, I want to satisfy the given condition up to the ith card, okay? So xi basically denotes the number of boxes which I need to buy if I have to collect the ith new card. So I assume that I already have I-1 cards, new cards, in some order. They could be repeated, I don't care. But the ith new card is the final one I will take. And that is denoted by xi. That random variable is denoted by xi. So to give some examples, so if I buy one box, just one box, it's guaranteed that I'll get a new card because that is my first card. Okay. So x1 is always 1. That's it. And with what probability it occurs? It occurs with a certain probability. I'm assured to get a new card. Okay. There are no defects in the manufacturing. So I am assured to get a new card. So E of x1 is just 1. The value of the random variable times the probability of the random variable. Now, things get complicated from here on. So what is x2? So x2, we could get any of the old card. x2 is a sequence such that I require my sequence to have only 2 distinct cards. Okay. And I could have any number of old cards. Let's say I obtained the first box. I got some card. Let's say A. I got card A. I got a second box. Again, I got A. But on the third box, I got a card B. Okay. So this is an example of x2, something that x2 can have. One possible outcome. or I could have obtained just AB. Then also I'm done. Okay, or AAB, AAB. Okay, so these are some examples that X2 can take, where A and B are denoting cards. Okay, so what I say is that with X2, I get an old card with probability 1 by n because there is only one card. To get that card, that's probability is 1 by n. And to get a new card, I have a probability of n minus 1 over n because there are n minus 1 favorable events for my X2. So if you think carefully, let me write it properly and I can see that. So just keep A fixed, okay? Just forget about A. Start from here. So if I got a B, I'm done. I'm happy. I got a new card. I could get AB. I get a card in the third box. Or I could get AAB. Or I could have gotten AAB. Okay, and so on. So if you recall the coin tossing experiment, let's go back once again. This is exactly like this. I could have obtained H. I could have obtained H. I could have obtained TH, TTH, and so on. Okay. So my X2 is similar to a geometric distribution, right? My X2 is similar to a geometric distribution. Okay. Now, what is the probability? What is the favorable probability? I said that I can obtain a new card with this probability. So this is my favorable probability. So X2 obeys a geometric distribution of parameter n minus 1 over n. Okay. Now, I could repeat the same argument for X3. Oh, okay. And what is the expectation value of X2, which is 1 by P, which is n over n minus 1. I could repeat the same argument with X3. Okay. How? Let's say I have obtained AB. I'll fix AB. I forget about AB always. I forget about AB. Then I could obtain C. Okay. Or I could obtain AC. Or I could obtain BC. I don't care. Or I could obtain AAC, some ABC, let's say, or so something, so on. So you see that this is again reducing to the problem of geometric distribution. But now things are a bit different in the sense that I have 2 by n probability of getting an unfavorable event. What are those unfavorable events? A and B. Okay. And what are the favorable events? Those are n minus 2. Total cards is n. So n minus 2 are favorable outcomes. So the probability of getting a new card is n minus 2 over n. So X3 obeys a geometric distribution with this parameter. Okay. In general, I can keep repeating this argument. Xk will obey a geometric distribution of something like this, n minus k plus 1 over n. Okay. If you do not understand this, go through this argument carefully again once you go back and think about it. Okay. It will be a geometric distribution over and over again. Now, all the xi's are independent, right? I don't care, all are mutually exclusive. So 1 is not equal to 2. So naturally, first card and the second card are not equivalent in that sense. Like I'm giving a very lame example, but that's what I mean. So each of these xi's are independent. So I can just add the expectation value. This expectation value of the whole variable is just the sum over the expectation value of the individual variables. So what I obtain is this quantity, this summation over. So n by n plus n by n minus 1 plus so on by n by 1. And if I take n common, I get a series like this. And this series has a well-defined formula, which is approximately log n plus gamma, where this gamma is something called the Euler-Mascheroni constant. Okay. So on average, I have to buy n times log n plus gamma boxes to ensure that I have at least one of each card. So that's the essence of this problem. So I have to find this expectation value. Okay. I hope I was not, I think I was not very clear, but if you have any questions that you want to, like any particular step you want to understand, you can ask.
Yeah, sir, like how E2, like,
Sorry?
so like E2, sir,
I'm not able to hear you. Can you speak
yeah,
louder?
like E of bracket of X2 is equals to n by n minus 1.
Right. So if you remember, let's go back to the coin tossing experiment. So expectation value of this geometric distribution is 1 by p. P was the favorable outcome. Favorable outcome is probability is p. Unfavorable is 1 minus p. So now xk, each of the xk is a geometric distribution. And what is the favorable outcome? N minus k plus 1 by n. So sum over, so x, if you recall, it was x1 plus x2 plus so on up to xn. Okay. So because each of them are linearly independent, so like each of xi is independent of each other, I can break up this E of x into sum over expectation values of xi's. Okay. Because of this linear property. Okay.
Okay.
And each of the expectation value, I know what is the formula. It is 1 by the favorable probability. And each of the favorable probability is n minus k plus 1 for the kth random variable. So this is n by n minus I plus 1. And I just expand the sum. That's it. That's what I've done here.
Okay. Okay.
Yeah. Anything else? You should go over this problem again. This is one of the more advanced problems, but it is useful to know this. Sorry, I could not hear you. Could you repeat? Hello? 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 Am I audible?
Yeah.
Yes, sir, you're
Yes,
audible.
sir.
Okay, I think I lost. This person who was asking the question lost their connection. So if you have any question, let me know. I'll come back to this. Okay. Okay. So moving on. So let's consider another problem, which is like I construct all the 6-digit numbers out of only 3 digits. So ABC can take values from 0 to 9. So ABC are distinct digits, and the sum of all these digits is given to me. Okay. Now I want to find what is the largest remainder when the 3-digit number ABC is divided
Sir,
by.
can you please?
Yeah, sure. Tell me. I'm not able to hear you. Could you just type in the chat what you are trying to ask? That would be faster, I guess. Hello? Is it me or is it the other person who has lost the connection?
No, you have the person only.
Okay.
Write the question in the chat box.
Yeah, they can just write the question in the chat box and I'll have a look. Okay.
Now go to the next problem. That is.
Yeah.
We'll come to this problem again.
Yeah, sure. It's okay. So I'm trying to construct. Sorry. Maybe we can discuss the problem again at the end of the session. Okay.
Okay, sir.
Yeah. Okay. So I'm trying to construct 6-digit numbers out of ABC, which are 3 distinct digits. And I'm given that the sum of all possible such 6-digit number is given to be 5, this quantity over here. Now I want to find the largest remainder of ABC, which is like ABC is equal to 100A plus 10B plus C. Given that it is divided by 100. So I want to see what happens. What is the largest remainder this can have? Okay. So ABC is this quantity over here, and this is congruent to 10B mod C. So 100 divided by 100 is 0, so I don't care about that. So I am trying to maximize 10B plus C. Also note that ABC can only belong to this set, 1 to 9. And I would like you to figure out why it cannot be 0. Okay. I think it's pretty much obvious, but okay. So we want to maximize 10B plus C. That is the remainder when ABC is divided by 100. Okay. But I'm also given that the sum of the 6-digit numbers. So there might be some constraints on this quantities A, B, and C, which I must check first. So I claim that the sum of these 6-digit numbers consisting of ABC is given by this quantity. Okay, A plus B plus C into 10 to the power 5 plus 10 to the power 4 plus 10 cube plus 10 square and so on times 3 to the power 5 equals to this. I'll give a justification in a smaller case, but take my word for it, you should verify it on your own. Okay. So this is the constant that I obtain on ABC. Okay, once I solve for everything, this is the constant I have on ABC. Now to maximize 10B plus C, subject to this condition, I can easily choose B is equal to 9 and C is equal to 8. And this choice is valid because I also have a non-trivial solution for A, which is 5. So the largest remainder is 98. So the only part left for me to do is justify that this sum is the correct sum. So let me do that for you, but in a simpler setting. So let's consider only 4-digit numbers, and we have constructed them out of A and B, 2 distinct digits. A is not equal to B. Okay. So what are the total possibilities? There are 16 in total, and I've listed out for you. So now I have to add up all these numbers. So that also I've done for you. So A occurs in the first place, in the thousands place, 8 times. So A into 10 cubed into 8. Similarly, B occurs in the thousands place 8 times. So 10 cube into 8. And you can verify for the rest. So this reduces to A plus B into whatever quantity I've written, 1111 into 8. And this is exactly similar to what I had here. A plus B into 11111 into 3 to the power 5. So I tried to construct 6 digits. So I ended up with 3 to the power 5. Here I'm trying to construct 4 digits. So I end up with 2 cube. Okay. So you should verify this in general. This is a nice exercise you can do. It just requires the knowledge of decimal representation of numbers. Okay. So you should do this exercise. So the answer that you get is 98. Okay. Any questions regarding this?
So why C cannot be 9?
Why C cannot be 9? What was our question? A, B, C are all
Distinct.
distinct. So can C be 9?
No. And so why 3 to the power 5?
Yeah, that is left as an homework, right? So you should see why 3 to the power 5. I've given you some hint over here. I've given some hint over here. You should check why 3 to the power 5. Okay. It's an exercise in multiplication principle and decimal representation of numbers. You should do that. Okay. Anything else?
No, sir.
Okay. Moving on. So this is another important problem. I'll introduce many concepts. So if you don't understand all of them, it's fine. I think other teachers will take over. So these are some common functions that are used in number theory Olympiad problems. So this is the Euler function. This is called the divisor sum of divisor function. And similarly, tau of n is another function called the number of divisors, okay, of n. And you'll need something called a Mobius inversion formula, which I'll show you. Mobius inversion formula and transformation are the same. And you'll need something called the Mobius function, which also I'll introduce. So let me write down phi of n, sigma of n, tau of n, and Mobius function is denoted as mu of n. I hope you are all familiar with the Greek symbols. Okay. So this is a alpha, beta, gamma, delta, eta, epsilon. This is phi, sigma, tau, mu. This is nu. Okay, so these are some common symbols that I will be using. If you don't know what that means, ask me. And then there will be something called omega of n and capital omega of n. So, okay, so these are the 6 arithmetic functions. These are called arithmetic functions that I'll introduce in this problem. Okay, so keep track of them. Okay, let's start. So tau of n, as I already said, it's the number of divisors of n. It's an example of what is called an additive function. I'll explain what an additive function is. It's a class of arithmetic functions. These are all arithmetic functions. And then there is sigma of n, which is the sum of the divisors of n, which is shown to be the sum over divisors, such that d divides n. And this is an example of what is called a multiplicative function. This is also what I'll explain in a future slide. And then you have phi of n. I guess it's you have heard this in Anupam Shoikesa's lecture as well, which is number of primes, co-primes to n, which are less than n. Okay, number of numbers which are less than n and co-prime to it. So another important exercise for you, if I have a prime factorization representation of n in this way, then show that the number of divisors of n is this, the sum of the divisors is this, and the Euler function is given as this. So you should show this three relations. Okay, these are important exercises. Okay, so I said something called arithmetic function. Arithmetic function is simply a function whose domain. Have you been taught functions? Domain, codomain, range. Okay, just to give a brief idea. So you have some set A and some set B. So a function is something like a thread that you associate from one set to the other. Okay, and every thread can have only one endpoint. Every thread starting in A can have only one endpoint in B. Okay, so that's an example of a function. Then I say that the collection of A is called the collection A is called domain. The collection B is called codomain, and all these thread endpoints. Let's say I have some these endpoints of the threads are called range. Okay, so these three terminologies you should keep in mind: domain, codomain, and range. Okay, so domain is the collection of all the points where the threads start. Codomain is the where you go to, and range is all those endpoints of the thread. Okay. Okay, so arithmetic function is just a function whose domain is natural number and codomain is some subset of complex numbers. And they may be required to satisfy something called an arithmetical property. Arithmetic is just plus, minus, into, and divide. So some sort of an arithmetical property it has to satisfy. So I recall that I said that tau is an example of an additive function and sigma is an example of a multiplicative function. So these are examples of arithmetic properties. If a comma b is in natural number such that the GCD of a and b is 1, then sigma breaks up into this form. Okay, this way. So sigma of AB breaks up into sigma of A times sigma of B. So this is an example of what we call a multiplicative function or multiplicative. This is the multiplicative property of the function. And in general, it's an arithmetic function such that this happens. So if it satisfies such a relation, then it's a multiplicative function. And arithmetic, as you would have already expected, instead of multiplication on the right hand side, I should have a plus sign. Okay, so what is a Mobius function? So Mobius function is given by this definition, and alternatively it is given in terms of omegas. Okay, I'll explain what omegas are. So mu of n is plus 1. It can take only 3 values. So the range of Mobius function is plus 1, minus 1, and 0. And the domain is the set of all natural numbers. So mu of n takes plus 1 value if mu of n is square free. I'll explain what square free means in some time. And if it has even number of prime factors. Okay. It takes value of minus 1 if n is a square free number and it has odd number of prime factors. Okay. And finally it takes value 0 if it is a square, if it contains some sort of a squared prime factor. So to give some examples, and by definition, mu of 1 is 1. Okay, so this is some exclusive case, but beyond that, mu of 2. How many prime factors mu of 2 has? It has only one prime factor. Then its value assigned is minus 1. Mu of 12 is mu of 2 square times 3. So you notice this 2 square appears. So this is an example of a non-square free number. So I'll explain what square free in some time, but you should keep in mind that 12 is an example of a non-square free number. So I should assign a value of 0 to this. Now mu of 42 can be written as 2 into 3 into 7. Each of the primes occurs exactly once, and there are odd number of primes. So it has assigned a value of minus 1. Mu of 22, it contains 2 prime factors, 2 and 11, and each of them occurs exactly once. So it has a Mobius function of plus 1. So you can think of more examples and look up other references for it, like the one suggested by Manjil yesterday, David Burton. So what was omega n and capital omega n that I told you? These are another examples of arithmetic functions. Omega n is the number of prime factors of n. And this is an example of what is called an additive function. So additive function is an arithmetic function such that if GCD of AB is 1, f of AB is f of A plus f of B. This is called an additive function. Omega of n, on the other hand, is the number of prime factors of n, including the multiplicities. So for example, omega of 12 here is 2 square into 3, it's 1 plus 1. 2 and 3 are the only prime factors of 12. So there are 2 in total. However, capital omega of 12 is 2 square times 3. So there are 2 occurs with multiplicity 2 and 3 occurs with multiplicity 1. So in total, it's 3. Okay. Now I said that capital omega of n is totally additive. What I mean by totally additive, if you remove this condition, GCD of AB is 1, and still it satisfies that f of AB is f of A plus f of B, then it's called totally additive. Okay, it's just some definition, you did not bother about it. Okay. And what is a square free number? I think I've already explained it. It's an integer which is not divisible by any square number. So 12 was divisible by 2 squared. So it's a non-square free number. So naturally, 6 is an example of a square free number. 10 is an example of square free number. And if you notice the pattern, you can see that n should be written as a product of primes with 1 power. Okay. So then such a number n is a square free number. If any prime is squared, it becomes a non-square free number. It's no longer square free. Okay. So this is an important property of square free number, or you can say it's a definition of square free numbers. Okay. So I also mentioned something called the Mobius inversion. What is that? So f and g are 2 arithmetic functions that is given to me, and they satisfy this property. G of n is sum over d dividing n f of d. Okay, for all natural numbers n. Then the Mobius inversion of g and f is given by this. So you express f. So initially g was expressed in terms of f. Now you invert it and write f in terms of g. But there is this Mobius function sitting here. So that is why I needed to introduce the Mobius function, and that is why this identity is called Mobius inversion. It was introduced by Mobius. Okay. So is it clear? There was lots of definitions, but I hope you can go through it again. But the idea is this Mobius inversion. Okay, and some property of the Mobius function that I'll come to. Okay. So now let's return to our original problem. We want to see for which values of n this is true. Sigma of n plus phi of n is 2n. Now, this is a property of the Euler phi function, and I'll ask you to prove it in general, but I'll show you a simple example why this should hold. Okay. So if you compare this and this, you compare this and you compare this. So g of x, here g is x, simply the identity function, and f for me is the Euler function. So is it okay? So just comparing the two things. So what is the Mobius inversion? I should be able to write phi in terms of n. So that is what I've written. Phi of n is equal to Mobius inversion of n by d. So this is what we had, right? G of n by d. So instead of wherever I see x, I'll put n by d. Okay. Now I should justify why this holds. So I'll do that for the case of n is equal to 10, a simple case. So let me start with this set A of fractions in this form. Okay. So I take the denominator always to be 10 and I write all the numbers up to 10 in this way. And that I'm calling the collection A, set A. What I'll do is, so I hope you know what is union, intersection, and those things, right? Is it been covered already?
Yes, sir.
Yes, sir.
Okay, good. So now I can write this set as a union of some smaller sets in such a way that I express every fraction here in terms of lowest fraction. So lowest fraction means numerator and denominator are co-prime. Okay. So I express this in this way. One set is this. This is the collection of all which are co-prime to 10. This is the collection of numbers which are co-prime to 10. Sorry, the numerator is co-prime to 10. Then I could have removed a factor of 2 in the numerator and denominator, and I end up with all those numbers which are co-prime to 5. Also, I could have removed a factor of 5, let's say here. And then I end up with all the numbers co-prime to 2, and 1 is by itself. Okay, this is 1. 10 by 10 is 1. So notice a pattern here. Okay. So I have divided the whole set A into smaller sets which are like something like co-prime to 10, co-prime to 5, and co-prime to 2. And 1 was by itself there. 1 is co-prime to every other number. So naturally, these are all empty. Their intersection is empty. So no two sets have any overlap. They don't have any overlap. So the sum of the cardinality of A can be written as the sum of the cardinalities of individual sets. And if you notice, what is the cardinality of this set? This set contains all the cardinality of this set is the number of primes, the number of co-prime numbers which are smaller than 10 and co-prime to 10. Okay. So this is phi of 10. So I've written, and the original set had a cardinality of 10. A1 had cardinality 5, 10. Similarly, A2 had phi of 5, A3 phi of 2, and A4 phi of 1. And this is nothing but all the divisors of 10. So 10 divides 5, 10 divides 10, 5 divides 5, 2 divides 10, and 1 divides 10. Okay, so these are all, this is what I had set out to prove. 10 is equal to sum over Euler function over the divisors such that D divides 10. And it's an exercise for you to prove it in general. This is not a very difficult task. You should be able to do it in a similar way that I've done here. Okay, you write, so let's say you want to do it for n. You write 1 by n, 2 by n, so on up to, let's say n by n. And then you divide in terms of lowest terms, lowest fractions. And you consider all such categories, different categories. Okay. So let's return to our original problem now. So sigma of n can be written as this. This was the first expression that I had shown you. It's just the sum over the divisors. And alternatively, I could write d prime equal to n. So if d prime divides n, this implies n is equal to some d prime times d. What is this identity called? That any number a can be written as bq plus r, where this is less than r less than b. What is this identity called or relation called? I hope you have done this. A comma b belongs to natural. Have you done this? Euclid's lemma?
Yeah,
Or
yes. Yes.
Yeah. So I'm using Euclid's lemma here. Since d prime is dividing n, the remainder is 0, and I'm calling q as d. Okay. So I could write d prime as n by d. Also notice that the initial sum was over d prime, but I've written it as sum over d. But that is always true, because if d prime divides n, so does d, right? D divides n with quotient t prime. So these two are equivalent. Okay. Now sigma of n plus phi of n can be written in this way, and I want it to be equal to 2n. That's the requirement. So I separate from, so every number, 1 divides every number. So I separate out this part, and I have the rest of the sum. This must be equal to 2. I have cancelled out n from both the sides. So this must be equal to 2. And if you recall, I said that mu of 1 is assigned a value of 1. So this is in total 2. So this 2 and this 2 also cancels out. So this sum has to be equal to 0. But when can this be 0? If mu of d is equal to -1 for all d dividing n and d is greater than 1. And if you think about it a little, this can only happen if n is a prime to begin with. Okay, I'll let you think about this. Spare some time, think about it. and see that you cannot come up with a counter example. So if n is not a prime, if n is not a prime, then there exists a d which divides n such that mu of d is equal to +1. Okay. So this can happen, this result can hold only when n is exactly a prime number, otherwise it cannot hold. Okay, so you should think about this. Any questions regarding this? There are many definitions. You should carefully go through the definitions because it is assumed that you'll know such definitions for Olympiad problems, sigma of n, phi of n, and all those things. Okay, so you should go through them. I hope there is no doubt. If you have anything, you can ask me later. Okay. How am I doing on time? It's only 10 minutes living. Okay. Fine. Yeah. Okay. We're not even halfway through. Okay. So this is a simpler problem. You want to find the number of points of intersection of n straight lines, given that n is satisfying this equation. And similarly for circles and lines together. Okay. It's a simple problem in permutation and combination, and you'll require quadratic equation as well. Okay. So when two lines intersect, they can do so at most at one point. Like I'm not assuming coincident lines. They intersect at infinitely many points. I'm not assuming that scenario. I assume that they intersect at unique point. So each intersection of two lines give you 1 point. So essentially, the total number of points when n lines intersect reduces to the problem of choosing two lines out of the n lines. Okay, that will give you the number of points. And this can be done in n choose 2 ways. So now I have to, so the given n also satisfies this relation. This I can just solve for. So I hope you know what is the meaning of A, P, B. The number of permutations of B objects, A objects taking B at a time. So this is just A factorial divided by A minus B factorial. I've assumed A to be greater than or equal to B. Okay. Okay, so I've just used that formula and I've expressed the properties of factorial. So n plus 5 factorial can be written as n plus 5 into n plus 4 into n plus 3 factorial. Okay. So I've used that property here and I've expressed everything in terms of that. And if you do some algebra, you'll end up with this equation. And simplifying gives you this, which has roots this. Do you know how to solve quadratic equations?
Yes, sir.
Okay, good, excellent. So if you solve this, you will end up with this. So there are two possibilities for n, and hence there are two possibilities for the number of intersections, 15 or 21. Okay. Okay. Now there was also a question what happens when two circles intersect. So two circles can at most intersect at two distinct points. I'm not assuming two coincident circles. So the maximum number of points the n circles can intersect is equal to twice the number of ways of choosing two circles out of the given n circles. So this is two times n choose 2. And the third one, I'll leave it to you. When everything is there, you have n circles, you have m lines, and they intersect among each other. What is the total number of intersections that you should find? Okay. Okay. So this is okay. How am I doing on time? This will take a lot of time. So I'll explain a few things. So do you want me to continue like around up to 10:45 or something? Is it okay? Police,
Yes,
sir?
sir.
Okay, great. Okay, so let's see what is this. So ballot means some elections are going on and there are two candidates P and Q, which score Q votes and P votes. Okay, Q scores Q votes and P scores P votes, where P is assumed to be greater than Q. Then show that the probability that throughout the counting process, P was always ahead of Q, that can be done, that is true in this way, P minus Q by P plus Q. What this means is that there were P minus Q favorable outcomes with respect to P plus Q possibilities. Okay, there could be more, but basically this is what it means. I'll explain what it is. So this can be done in many ways. I will show you two proofs here. One uses something called the cycle lemma. I'll explain what that is. And the other one is mathematical induction. So yesterday there was a question on mathematical induction. So I'll get into what mathematical induction is. But here we will use mathematical induction for two variables. I hope everyone is in class 9 and 10 now, and or maybe 11 students also. So if you have access to R.D. Sharma's class 11 book, there is a problem on mathematical induction containing two variables. Okay, so you should check it out. So I'll be using mathematical induction of two variables. Okay, so let's see first the cycle lemma, what this cycle lemma is. So here I'm giving you a simple form of cycle lemma. There is a generic form as well, which I'm not getting into. Consider a sequence of m plus n elements. Let me change the color. So consider a sequence of m plus n elements such that there are m a's and n b's for which m is greater than or equal to n. Okay. So a generic, I told you I'm using a simple form here. In general, it can happen that m is greater than or equal to kn. Okay. For some k, positive number k, positive integer k. Then cycle lemma says that there exist exactly m minus k out of m plus n cyclic permutations of this type. Okay, what is a cyclic permutation? So let's say I have a1, a2 up to ax, let's say, or ap, let's say. So what is a cyclic permutation? Cyclic permutation is something like this: a2 dot 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 ap, a1. This is one cyclic permutation. Next cyclic permutation could be something like a3 dot 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 ap, a1, a2, and so on. So these are examples of cyclic permutations. And if you have, like, the examples that I've shown you is one shift, just one shift in a particular direction. So there are p such cyclic permutations. For a given sequence of length p, there will be p cyclic permutations. Okay. And you might have also heard of something called circular permutations. You should not confuse it with circular permutations. You are welcome to check books on what is circular permutations. It's just permutations on a circle, that's it. But let's not get into that. So I'm taking here cyclic permutation, means one shift. Okay, I'm just shifting by ones. So the sequence length is m plus n. So naturally the number of such cyclic permutations is m plus n. And what cyclic lemma states is that m minus n out of those m plus n sequences are dominating. I'll explain what dominating is. So I call a sequence P1 up to PL of A's and B's, where A and B are some distinct objects. Here in our case, it was candidate P and candidate Q, or the votes for candidate P and candidate Q. I will call this sequence dominating with respect to A. I should have written that dominating with respect to A. If for every position in this sequence, I can range from, if in every ith position, 1 less than equal to I less than equal to L, the number of A's in this P1 up to Pi, the shorter sequence, is more than the number of B's. Okay, so let's see some examples. So this is an example of L is equal to 3. Here L is 3. L is equal to 3. This is an example, L is equal to 5. Okay, so AAB is an example of a dominating sequence with respect to A. So let's check why. The first position is A. That's good. Second position is A. That's also good. No B so far. So 0B, 2A. Third position is 1B, 2A. So still I have more A's compared to B's. But the second sequence here, ABA, is not dominating because at the second step, the number of A's and the number of B's are each 1. But I require that at every position, its number of A's is more than. This more than is important. It's not more than or equal to, but more than the number of B's. So this is an example of a non-dominating sequence. with respect to A. I hope this is clear. Another example, let's say a bigger sequence. So this is in this position, A is 1, B is 0. Good. In this position, A is 2, B is 0. Still good. Here, A is 2, B is 1. Still good. In here, A is 3, B is 1. And over here, A is 3, B is 2. So this is an example of a dominating sequence. A number of A's at every position is more than the number of B's. So this is an example of a dominating sequence. But the next one is not. It fails at this point. Okay. All right. Okay. So let's come back to our original problem. We want to find such dominating sequences for P. That is the problem. Okay. We want to find dominating sequences for P. So we call a ballot sequence dominating if candidate B is strictly ahead of candidate Q throughout the count. Okay. Then invoking cycle lemma. So cycle lemma says that any sequence of P P's and Q Q's such that P is greater than Q has precisely P minus Q dominating cyclic permutations. Let me explain what this means. So in total, how many sequences, cyclic sequences can we have? P plus Q. Okay, so P plus Q. I should not write this. Okay. All right. Let me show you via an example where there are 4 P's and 2 Q's. Okay. All right. So I arrange them on a circle. And what I do is I remove pairwise PQs. Okay, I remove them. Then at the end of the day, I will only be left with P's because number of P's were greater than number of Q's. So the claim of the cyclic lemma is that each of this, so also when putting them on a circle, I have to assume an order. So here I am assuming a clockwise order. Okay. So they go in clockwise direction. So cyclic lemma states that each of this P, the remaining P's, if you start your sequence from this point, some sort of shifted sequence, if you start it from this remaining P's, each of them will give you a dominating sequence in the whole P plus Q sequence. So what I say is that if you start out with, let me insert a page here. Okay. So here I had P, P, Q, P, Q. Something is missing, I guess. P. Okay. So begin with P was 4 and Q was 2. This is my scenario. What cyclic lemma states that pairwise you remove adjacent PQ. You remove it. So you will be naturally left out with 4 minus 2 elements. Okay. Now, cyclic lemma states that if you had started your sequence with, let's say here, P1, 2, 3, 4, 5, 6. So if you had started with the position 1, P, and you go in the cyclic direction, you're bound to end up with a dominating sequence. That's a guarantee. Similarly, you could start with this P as well. You'll end up with a dominating sequence. So that's what I'm trying to say here in a generic case. So our case was P and Q. So we arranged all the such P's and Q's on a circle. And then you will remove adjacent pairs of PQ. So PQ pairs, adjacent PQ pairs are removed. You'll be left with P minus Q of P, capital P. And then the cyclic lemma states that each of these P can serve as a starting point of a dominating cyclic permutation. And that's what we require, the number of dominating cyclic permutations. Okay. So how many of them are there? So total number of sequences are P plus Q, cyclic permutations. And the dominating among them is P minus Q, because there are P minus Q starting points for such a dominating sequence. So the natural number of favorable outcomes is P minus Q and the total number is P plus Q. So the probability is P minus Q over P plus Q. Is it okay? You want to find dominating sequences. The claim is that after removing the PQ pairs, whatever P you are left out with, you can choose that as your starting point in some clockwise or anti-clockwise direction. And then you'll end up with a sequence that is dominating in the whole sequence. That's what I've written here. Okay. If something is not clear, you should go over this, whatever I've written here once again. And I think hopefully it will make more sense. Okay.